This video is going to teach you how to use the equilibrium state and the idea of a net force to find out what missing forces are acting on an object. So in the equilibrium state, objects are either inferred or required to have all forces balanced. So in our problem here, we have a 10 Newton box with an 8 Newton box resting on top of it. It is sitting on the ground. So for our particular demonstration, we're going to consider this motionless. Because it is motionless, the motion is unchanging, we are going to infer that the forces on this must be balanced. Let's go ahead and do a force diagram to make sure we have all of the forces identified. So I've got my crate. I have a 10 Newton force down from the weight of the crate. I have an 8 Newton force down from the box on the top. And if I left it at this, the forces can't be balanced. They're both pushing the same way. This will fall, the motion will change. But it is resting on the ground. So unlabeled in the original diagram is the normal force from the ground. Now, if our forces are going to be balanced because we are in equilibrium, then this normal force must counteract all of the downward forces. So looking at it this time, just taking a look, it needs to be 18 newtons up. I'm going to show you what this looks like algebraically. So we are taking a look at our net force. However, because it is required or inferred to be balanced, we are setting it equal to 0. So this is our special condition this time. So I'm going to take all of my forces. I have the normal force. I'm going to combine it with the 10 Newton force and the 8 Newton force and require them to be 0. I'm going to do a sign check. Force normal is up, so I'm going to call that positive. These are down, so that's negative and that's negative. And then we're just going to do the algebra here. Force normal minus 18 newtons equals 0. So my force normal must equal 18 newtons. When I bring this over to the other side, it does become positive, algebraically showing me that my normal force is upwards, like we suspected in the diagram. And it does equal 18 like we figured real quick. Now, things can get a little trickier if we have things happening in two directions. So let's add over here a 12 Newton force pulling up and at an angle of 30 degrees. Let's put a 12 Newton force on there. So now we've got some really weird things going on. So we're going to redraw the force diagram, nice and big here. So now I have my box. I have 12 newtons this way at 30 degrees. I have 10 newtons down, and I have 8 newtons down, and I have a force normal up. I'm going to draw in a coordinate plane because I'm going in both the x direction and in the y direction. Once I've done this, my approach is essentially identical to the last one. I am going to take a look at the sum of the forces, but before I do that, I am going to make sure that I break my angled force to go with my coordinates. I'm going to do the math off to the side here real quick. My x-axis is going to be 12 cosine 30. So in the x direction, that is going to be 10.3. And in the y direction, that is 12 sine 30, or it is going to equal 6 newtons. So that's 6 newtons up. So if we are going to require this to be in equilibrium, the sum of the forces is equal to 0. except for this time I have to make sure it is in both the x and the y directions equal to 0. If either of these is non-zero, the object is not in equilibrium, the motion will change, and we have a slightly different problem. So in the x direction, I'm going to take a look at my picture here. I have 10.3 newtons to the right. So 10.3 newtons. I have nothing on my diagram, but that isn't going to equal 0. There must be another force acting on it this way to counteract it. If there isn't one, then we aren't in equilibrium. Looking over here, that other force must be friction, because without it, my box will start to slide. So we're going to add in the force of friction, and that equals 0. Now I suspect this is going to be negative, but I'll leave it alone for now. So I solve this out. Force of friction is equal to negative 10.3 newtons. So the negative did show up. It's right here. So that is a force of friction to the left of 10.3. Looking in the y coordinate axis, we have force normal plus 6 newtons minus 10 newtons minus 8 newtons equals 0, because we are in equilibrium. So we solve this guy out. Force normal, negative 18 plus 6, that's minus 12 newtons, is equal to 0. My force normal is now 12 newtons in the positive direction, which matches what we have here. We can also understand that it is not as large of a normal force as it was before, because this force here is pulling up a little bit. It is going to alleviate some of the force acting on my surface down here. It's going to lift it up a little bit. So the normal force doesn't have to do as much work. We're going to get a smaller number. So an equilibrium problem is just using the net force equation and definition. However, we are requiring it to be 0 because the motion is not changing. The forces are required or inferred to be balanced.